Davis Utilities and Engineering, and I'd like to kick off our next session, which is Global Examples of Living Labs. Today we have presentations from 3 different speakers, and they'll share campus examples from the Cooper Union, Berkeley National Lab, and UAB in Barcelona. I'll read a short bio before each of their presentations, but before we start the session, I wanted to go over some of the logistics for anyone that's recently joined. After the presentations are complete, there will be time for Q&A. However, if you have questions during the presentations, just be sure to add them to the Q&A box on the bottom of your screen, and then I will ask them at the end of the session. And as you know, the chat feature is available for any general commentary throughout the presentation, so feel free to continue to network and chat. So with that, I'll introduce our first speaker, Melody, who I'd like to invite to go ahead and queue up your slides as I share her bio. Let me stop sharing and give you control. So Melody Baglione is a professor and George Clark Chair of Mechanical Engineering at the Cooper Union for the Advancement of Science and Art. In New York City, Dr. Baglione teaches courses in the areas of process control, vibrations, and energy-efficient building systems. She has over 7 years of industry experience as a consultant and powertrain systems engineer. She regularly advises campus facilities on improving efficiency of heating, cooling, and cogeneration systems, retro-commissioning facilities upgrades, and other energy efficiency and decarbonization projects. So with that, I'll turn it over to Dr. Baglione to begin her presentation.
Thank you, everyone, for having me here. Can you see my screen? Trying to navigate here. Okay. All right. So, yeah, my name is Melody Baglione, and I'm a professor and chair of mechanical engineering here at Cooper Union. And I also have the appointment of Facilities Energy Efficiency Advisor. I do the New York City Local Law 84 benchmarking compliance reporting, and I also represent Cooper Union in our New York City Carbon Challenge and the NYSERDA, New York State Energy Research Development Authority REV Challenge for colleges and universities. A little background about Cooper Union. We were founded in 1859 by industrialist and philanthropist Peter Cooper. We have around 1,000 students majoring in architecture, art, and engineering with a 7-to-1, 8-to-1 student to faculty ratio. We were tuition free for 155 years until 2014, when faced with some financial difficulties, and the scholarship levels were reduced to 50% at a minimum, sometimes more. With our financial health back on track and through donations, the average scholarship level is now at 85%. And just this year, Cooper Union announced that we would be 100% free for seniors until 2028, when the plan is to be returned to free for all students. In 2009, we moved into 41 Cooper Square, a state-of-the-art 186,000 square feet LEED Platinum certified academic building by Morphosis. The building has 2 500-ton chillers, natural gas-fired boilers, heat exchangers for radiant ceiling panels, water and air side economizers, a 250 kilowatt cogeneration plant, which is at the time not operable, exterior mesh double skin that intends to reduce the heat gains and losses. And in previous sessions that I've presented at, we identified needs and opportunities for project-based learning, and mostly that our students need to see the real-world applications of the theory that they're learning, and the opportunity to apply fundamentals and a systematic approach to the design and operation of low-carbon buildings is crucial to that. And how better to do that than to engage them on projects on our campus or on competitions with faculty, staff, and professionals. So some of the ways that Cooper Union has done that is we've had students contribute to our 40% carbon reduction by 2030 roadmap and our climate action plan. They've developed data historians and energy dashboards and reporting tools. They've modeled and implemented and evaluated different energy saving measures, such as condenser water reset, which I will talk about today, other things such as static pressure reset in our air handlers and temperature and airflow setbacks. They're also engaging in the design of high performance, low carbon buildings and competitions. And more recently, we started a partnership with a local community organization and extend our energy modeling to the community scale through distributed energy, battery, solar and battery modeling, and looking at solar potential with some government partners. So through all of this, we've again achieved some carbon reduction. In 2007, we agreed to be a part of the New York City Carbon Challenge, which at the time was voluntary. We did reduce our energy consumption by moving into the new LEED Platinum building that we are now in. However, it's slowly, the carbon footprint and the energy use intensity slowly crept up until we peaked in 2014. At that point, we engaged through a number of grants, NYSERDA, energy professionals that engaged us in climate planning, but also energy conservation measures and energy audits on campus that we actually had our students shadow. And we co-developed a course that is called the Energy Efficient Building Systems course that is still running today and being taught by energy professionals, where the students actually go out and take measurements on our campus and make recommendations that we then work with our buildings and grounds to enact. But since some of these initiatives are underway, we have been reducing our carbon footprint. We are still have some ways to go to get to our 40% carbon reduction target, but we've made tons of improvement in that regard. And in 2019, the New York City enacted aggressive climate legislation. So the carbon challenge is no longer voluntary. Beginning this year, there will be fines for based on buildings for not meeting the emissions targets set by the city. And those fines will increase again in 2030. At the same time, New York State has committed to achieving zero carbon electricity grid by 2040. So on that regard, not only are we meeting these climate goals, we are also saving money for our campus, but also engaging students and preparing them for professional skills for climate careers. We've had a number of publications and master's thesis projects, conference presentations, capstone projects, and also a website that gets a number of hits. I haven't updated that statistic recently, but the last time I checked, there was quite a few traffic to that website. I'm going to present now just one of the projects. This project started out, well, first of all, there's a number of different ways we do project-based learning. One of them being all mechanical engineering students, since I'm the chair of mechanical engineering, they all take feedback control systems, and there's a lab associated with that class where they get hands-on experience with test benches. But then we take them on mechanical room tours and we show them building automation systems, and they have a small assignment related to that. So they all get some exposure to the mechanical equipment rooms and also building automation systems, and awareness of the need for decarbonization in buildings. Then some students go on to do internships either on campus through work study or through community organizations. New York City has a Ladder for Leaders internship program where they can work in community organizations or through our career fair at actual companies. We have projects, capstone senior design projects that all students do, and we offer the opportunity to work on campus related projects such as building energy dashboards or studying electrification efforts or solar. We have students go on to do master's research, and again, in the new elective energy efficient building systems course, which is co-developed with the NYSERDA funding. Energy professional and myself co-developed this course where students are actually going around on campus and taking measurements and making, looking at pump efficiencies, looking at the control systems and analyzing versus weather and our utility bills. So I'm going to highlight one particular project today, a case study that was done over 2 course projects and then a master's thesis project that was presented at an ASHRAE conference. But another more recent in 2020, we adopted the vertically integrated project structure, which came out of a consortium of Purdue and Georgia Tech. It's where students can get credit for projects over multiple semesters, where they work on either faculty research or large-scale projects or competitions on interdisciplinary teams across schools, and they're advised by faculty, and they work on these 1-credit course projects over a number of semesters to accrue credits towards working on these projects. We have a number of different sections. One of them is the solar decathlon competition. Another one we call Smart Cities, where students can work on either decarbonization projects on campus or in our community. So, and I'll just highlight 3 examples of those right now. So one project started out as a energy efficient building systems course project. The students developed a model of our chiller plant and looked at condenser water supply temperature reset. So that work spanned 2 semesters and was validated as part of a master's thesis and presented at an ASHRAE conference. So this is an excerpt of that presentation. Essentially, the students took pump curve data from the manufacturer, chiller efficiency map, and cooling tower data. And they did a parametric study that considered the pump, chiller, and cooling tower power. They then subsequently used building management system actual data to also validate the manufacturer data. And they iterated for a number of different condenser water supply temperatures and found the optimal configuration and the optimal set point under various load conditions. This is just one example load condition. And they plotted that over various loads for our 500-ton chiller and various wet bulb temperatures, and came up with our building management system could only take sort of a formula to be able to set the condenser water set point. So they did a regression fit of the data and the optimization study and actually implemented that into the building management system so that it recommends optimal condenser water supply temperature. Our facilities manager wanted to make sure that we kept that regression fit between 68 degrees and 78 degrees Fahrenheit, so we'll not go outside of that range. And that was actually implemented into our building management system. And then we took, this is actual data. We have over 1,000 hours worth of data. Here's just showing 2 weeks, 1 week where the system was in a constant mode. You can see that here in yellow, the constant condenser water supply temperature set points. And then you can see the reset condenser water supply temperature reset set points in blue. And then you see the chiller and the cooling tower and the total plant kilowatts. Oops. And then the students then plotted the actual data using a Python and box and whisker plots for different load ranges, and showed that under all load conditions, the reset temperature, especially for the cooling tower power, but also for the plant kilowatt per ton, under all load conditions, the reset strategy achieved energy savings. To be able to model this, they then used a Python machine learning model, a 3rd-degree multivariate polynomial regression fit using the sklearn library in Python, and developed a model that compared at any given time the reset strategy versus a constant strategy. And this is the data showing for 1,000 hours of reset versus constant set points and their power consumptions. And for 1,000 hours, we found a 15% reduction in electricity, $4,000 in utility costs. So if you extend that over the cooling season, that would be about 30 tons of carbon reduction and about 14,000 for our 500-ton chiller. So again, this was all through started out as a project in the Energy Efficient Building Systems course. The first semester they used manufacturer data. The second semester they used actual building building management system power data from our chiller plant. And then as a VIP and master's research, they then validated it with actual data after our buildings and ground staff let us implement this into the chiller optimization code. Yeah, so that was a successful project that we highlighted and presented at the ASHRAE annual conference. Another way that we, again, do project-based learning is through competitions. So I wanted to share our solar decathlon team. We started in 2020. The first time we competed in the solar decathlon competition, we did the design competition. It was completely virtual, but we do this as part of a vertically integrated project structure in which architecture and engineering students from all majors, mechanical, electrical, civil, we've had chemical engineers all work together, and they get 1 credit. It's much more work than 1 credit worth of work, but at least they're getting some credit over, 2 semesters, they get 2 credits. And they compete in the solar decathlon design competition. In 2023, over 124 teams competed from 97 colleges, and there are different divisions. We competed that year in the education division. We won first place, and then we competed against the other division winners and won the grand prize for the commercial challenge. In August of 2022, the New York City mayor announced expansion of the Harbor School on Governor's Island. We had already been thinking we wanted to do a project on Governor's Island over the summer and wanted to expand the school. There originally were only plans to retrofit some existing Coast Guard buildings and military barracks on the island, but we decided we wanted to build a new building, and then subsequently the mayor's office also announced that they would be building a new building. So the students actually got in contact with the Harbor School principal and some teachers and understood their needs and came up with a plan to re-envision their high school and expand it to double the size of the school. They have a diving program and a sort of restoring the oyster reef in New York Harbor project. So the students had no pool. They had to travel to Brooklyn, take a ferry to do their diving program. So we expanded the school with a design of a pool and other research facilities. So the design connected their 3 buildings. They have an existing building, a retrofit of a barrack and a hospital, and then also a brand new building that added classrooms, a competition-sized swimming pool, gyms, labs, and workspaces. So you can see on the left, this is just an excerpt of the presentation for any of you that are interested in seeing the full presentation on the U.S. Department of Energy's Solar Decathlon website. The entire presentation and the design is out there. They're competing on 10 different challenges from architecture, durability, resistance, engineering, resilience, integrated performance, energy, embodied carbon, environmental impact, occupant experience, comfort, and market analysis. So the guiding concept was to create a new community place for the school through sculptured landscapes. The building was we looked at the 500-year floodplain and elevated for a boardwalk, made sure all the mission critical MEP systems were elevated. We reached a net zero design by integrating photovoltaic canopies. We were very mindful of reuse of construction material, have a green roof and rainwater capture. And you can see, I went too far. The design responded to climate conditions using floodwater, had structural resiliency measures and passive ventilation and energy piles, solar and geothermal. And the sawtooth roof integrated the structural and architectural and maximize the solar energy gains for the PV. The design consisted of all electric net zero buildings. In fact, put energy back into the grid with a negative 15 kBtu per square foot energy use intensity. And this project had students, architecture, civil engineers, mechanical and chemical engineers, and electrical engineers, all co-advised by engineering and architecture faculty. So one of the biggest challenges with this is that the students are getting either 1 or 2 credits for working on this. And they already have a very rigorous course load in their engineering and their architecture schools and their studios. So they did this all above and beyond those course requirements, but went to compete at the National Renewable Energy Lab. And this year, took the grand prize. So we're sort of extending some of the learning to our community. So students have worked on the carbon action plan for our campus, but we're extending that now to our Lower East Side neighborhood. The New York City climate legislation is for buildings over 25,000 square feet, but there are a lot of old tenement buildings or smaller buildings less than 25,000 square feet that this legislation leaves behind. More recently, the city has announced that some of the fines would be collected and given back to sort of affordable housing projects and decarbonization efforts. But long before that, there's a local community organization that's targeting buildings under 25,000 square feet and community affordable housing, senior housing projects in our neighborhood. So students started working on these projects, and they have a program through the city where they can do summer internships. So a number of our students have done summer internships, but also we've added this as a vertically integrated project where students have been working on energy modeling, both mechanical engineering and architecture students, looking at retrofits at the community scale, looking at community solar. At solar, we have sort of public spaces or community gardens that have solar. So this is a more recent project that we're working on. Students are developing air quality sensors, and they're trying to quantify energy, financial CO2, air quality impacts. They're looking at solar potential, rooftop albedo models, and a number of those. And a group this year is also entering these projects into the U.S. Department of Energy Solar District Cup competition. Yeah. So these are just 3 examples of many projects that we have on campus. Mainly, one of the biggest challenges is, integrating these into the existing curricular structure so that students have time to work on these projects, and encouraging the collaboration across disciplines. At Cooper Union, we have art, architecture, and engineering, and many of the engineers would like to work with the architects and vice versa, but it's not outlined in their curricular structure. So it sort of sometimes organically happens that they have projects together, but this vertically integrated project structure is a way that students from different majors can work together and be co-advised by faculty from different schools. There is a consortium, again, it's out of Purdue, out of Georgia Tech, where faculty can attend the consortium and have and exchange ideas and lessons learned from this sort of vertically integrated project structure. We've been doing this as, again, working with our campus facilities, being aware of what projects they're doing on campus, and communicating with them when we do campus tours or want to collect data. We do this through competitions. And one thing I would say is also taking advantage of external partnerships and sort of being aware. Cooper tries to make contacts within different government agencies like NYCHA, which is our New York City Housing Authority, or there's projects along the East River to build a floodwater barrier. So this year we're actually responding for Solar Decathlon, another actual RFP from the School Construction Authority. So this gives our students not only the opportunity to work on decarbonization projects, but they're actually engaging with government or community partners as clients for these projects. And through some of these projects, students have actually landed internships with the companies that have advised our students through, for example, in our Solar Decathlon, we had a solar company serve as an external reviewer for our design and then hired our student. We did energy audits in a community organization where our students shadowed the energy audits, and then the student, a civil engineer, was subsequently hired by the company. So I think this has benefits on many different levels. And yeah, at this point, I have some references here to some of the papers that we presented, also the competitions and the community organizations that we've partnered with, and also the Solar Decathlon. The full presentation is available online as well at this point. Thank you very much for inviting me here. I look forward to hearing about the other projects that are going on.
Thanks so much for sharing all those exciting projects and the collaboration that you have with students and local communities. That was really interesting to hear. So now I'll introduce our next speaker, Marco Pritoni. Marco is a career research scientist at Lawrence Berkeley National Laboratory, where he conducts research in advanced controls, data-driven modeling, and data analytics applied to buildings. He leads a team of researchers focused on optimizing building operations and building to grid interactions. Marco has a multidisciplinary background that includes mechanical engineering, building science, data science, and human behavior. He holds a PhD and MS in mechanical and aeronautical engineering from UC Davis, as well as a BS and MS in industrial engineering from University of Bologna, Italy. So now I'll turn it over to Marco.
Thank you, Alex, and thanks for inviting me. Go Aggies. So my name is Marco. I'm a scientist at Berkeley Lab, and I'm here today to discuss a little bit what type of work we do around living labs at the lab. And to be clear, what I mean by living lab is sort of an environment that has building and potentially distributed energy resources, where we test new technologies, and there's some educational component. So to present quickly Berkeley Lab, Berkeley Lab is one of the 17 national labs from DOE. It actually predates DOE when Professor Lawrence in the 30s created what was called the cyclotron, a particle accelerator at UC Berkeley, and got the Nobel Prize. And then he decided to expand his enterprise, and he found a place on top of the Berkeley campus hill that was unused and owned by DOE, and built the first building there, which is the accelerator that became the iconic building that is in our logo too. And it's the beginning of Berkeley Lab. In addition to particle physics, Berkeley Lab is also well known to be the place where sort of energy efficiency was born in the United States, thanks to Art Rosenfeld, who swapped his career from being a physicist to being an energy efficiency guru, and kind of funded the fundamental pieces of Berkeley Lab's research on lighting, windows, simulation tools, and other technologies. In the 80s, Berkeley Lab created the first generation of appliance standards that created appliances that every year got better, to the point that now a refrigerator uses less than half of the energy than it used in the 80s, saving about $55 billion per year. We also won the Nobel Prize, in large collaboration in the Al Gore research group. And overall, the energy efficiency work has led to 200 watts of energy savings. And I think everybody here is pretty familiar with the field and how we sort of benefit from this early research. Now, Berkeley Lab has more than 3,000 employees and $1.5 billion per year budget. In the micro area of Berkeley Lab, my group is under the energy technology area, building technology and urban system division, and building technology department. This is the core of my team. It's more than 10 people, all staff. And our sort of the area we work on is defined there. We aim to advance the development, implementation, showcasing of smart technology to decarbonize buildings and distributed energy resources. Now, the disclaimer here is that LBNL is not an educational institution, and our primary mission is not educating students. It's delivering value to the customers and the funding agencies. For this reason, and only for this reason, we never had students working with us. Well, we actually do, and we did. And the reason why we have students is through those collaborations that Melody was mentioning before. We often have funding and projects available for students to work on. We have internships and other forms of collaboration, such as we host students for design competitions or senior design projects. And these are some of the people that we're currently hosting and supporting, and some of the former students. My experience with living labs starts since I was in grad school. I spent my last year of my PhD in Josh Moore-John's office at the Energy Conservation Office at UC Davis, working with facilities and working on now 10 years ago, their first version of data warehouse and other tools like the one you see there called Moostat that allows students to provide thermal feedback. And so through that experience, I really interacted a lot with students, and we did research projects, my dissertation as a chapter on this experience. And as I graduated and became a scientist at the lab, I kept kind of working with campuses. I worked with UC Berkeley, where we did optimization, the first generation of software-based control algorithm applied to buildings in collaboration with Center for the Built Environment and CIE. We also work with our campus, which is another living lab. And we did also data warehousing. We did optimization of buildings with Sustainability Berkeley labs. So all these are examples of living labs where you had the students embedded in the groups that worked in the projects and developed or deployed these technologies. But then I also participated in other cases where things are a little bit more fuzzy. At UC Merced, we optimized the central plant and the huge thermal storage tank they have there, and we enabled the storage to be used to minimize carbon and to potentially shift the load in case of demand response. But we worked very closely with facilities there, but not with the students. The students were people that we introduced in the projects. At CSU Dominguez Hill, we work also with facility, our friend Kenny, but not with students locally. At Syracuse University, kind of the same. So my sort of question to the audience is, are these living labs where the students are not like living inside the environment? In my opinion, they are. Other cases that were sort of strange, and we worked with Cal Poly Humboldt, or CSU Humboldt, how it was called, to deploy a very efficient and demand-flexible microgrid in a Indian reservation. So the site was actually not the campus, but the students were from a different campus. So a living lab can live externally to the campus that sort of is feeding the students. And I guess the last challenge to the definition of living lab is what I call a distributed living lab. This is our project HP Flex that is being funded by California Energy Commission, by Southern California Edison and DOE as cost share. We are trying to test and demonstrate this new platform called HP Flex, which is an open source integrated advanced heat pump load control system that optimizes energy use based on building preference, occupant preferences, and responding to dynamic prices and DR signals. So this is long definition is basically try to define a software that goes beyond what's currently available for small commercial buildings. So the status quo of small commercial buildings is that heat pumps, in general, rooftop units that serve them and serve the load of those buildings are typically not connected or grid responsive, and they don't coordinate between multiple units. So what we were planning on doing is developing a platform that allows to respond to dynamic prices and at the same time reduce peak load, greenhouse gas emissions, and maintaining comfort. And I skip a slide because I think everybody is familiar here, but the reason why heat pumps are sort of the topic of the year for several years now, is that based on, if you look at the big picture publications and sort of pathways and blueprint from the Department of Energy, California Energy Commission, or even Southern California Edison, decarbonization in building goes through electrification and heat pumps. But heat pumps can create peaks in the morning. And so there's projection, for example, in California, that California will have a winter peak in the early morning when most of the systems electrified systems go online, in addition to having a peak in the afternoon in the summer. So are normal heat pumps flexible? And the answer is no, they don't. And for this reason, we're developing the software. So the solution that we're trying to create is an open source platform that different companies can pick up and use. And we have partners that are doing exactly that. The control system uses what's called model predictive control, which is an advanced algorithm that looks at future prediction of occupancy, weather, and other variables. And through a model, predicts exactly what is the combination of actions, control actions that optimize a specific objective. The objective could be minimization of greenhouse gases, it could be minimization of cost or other things. And at every time step, typically 10 or 15 minutes, the calculation gets re-updated. So it continuously optimizes looking at the future. We want to test this algorithm before deploying this in real buildings in FlexLab, which is a flexible platform at Berkeley Lab that allows you to configure a specific building kind of in the way you want it, and having two cells that are identical, and you can compare a baseline technology with what you want you're testing. And then this is followed by installation of these controls in 6 field sites in California. And then, and I think this is the piece where the Living Lab becomes, touches people, is developing curriculum from training and education. And so I define this as a distributed Living Lab because the facilities belong in different places in California. 2 of them are actual campuses, but the data that we get from them and the control that we can do on them can be worked on and sort of used by students. Some early results are pretty compelling. As I said, we tested in FlexLab. We accidentally also had another project in Niagara using the same technology. And then we tested at UC Davis, which is one of the 6 sites that I cited before. And I said encouraging because the technology in the winter is able to shift the load, producing cost savings, peak load reduction in the order of 20 to 30%, which is pretty encouraging and consistent. So we used the lab to test kind of the viability, and we had consistent results throughout. Other things that we learned that I think are interesting is the things that don't work. So in one of these installations, the site experienced several difficulties. And those were obviously, well, they called us and said, your control system doesn't work. But some of the sort of culprit there were the sort of heat pump installation was not proper. The onboard controllers were not set up correctly, and some of the problems we generated with our control system. On the left, you see some of those that got sort of recorded and documented and resolved, and then discussed with the site. So this is one of the fundamental pieces, I think, of doing field tests and especially in living labs, which is what you learn should be fed back to the knowledge of the community. And how we're doing that in this case is through 2 different pathways. We were working with the BEST Center, which is a UC Berkeley-based center that develops a curriculum for community colleges. They work with about 70 to 80 different community colleges and develop the classes, the courses, and the material. And so we're working with them in the kind of context of train the trainer. And we will develop a curriculum about heat pump installation, maintenance, and practical elements that typically technicians have to deal with. And this is based on the feedback and the lesson learned that we got during the tests. With UC Davis, instead, we're targeting different activities at undergrad students and grad students. So we have a project-based class, which is the Path to Zero Net Energy with Professor Kornbluth, who was here before. We're going to offer a class to the students, or we're going to have participation in another fundamental EE class, and we're going to do capstone projects with the mechanical engineering department. And those are going to all be based on the real data from real building, which are, in this case, not co-located with the students. So this concludes my sort of review of this type of project, but I want to leave the audience with a couple of thoughts. Number one is, as a national lab, we love to work with university and have students, I was joking at the beginning, and teach them how to do things, and all our activities are project-based. So we invite people here who want to work with us or have students to send me an email. My address will be in the last slide. And we're happy to work with you and describe the project we have and possibly recruit students as interns. The second thing is pretty exciting. We just got awarded a grant from the California Energy Commission that is looking at large commercial buildings in campuses. So the previous project that I mentioned is heat pumps in small commercial buildings. This is buildings that have built-up systems. And we're going to work with 4 universities: Contra Costa Community College District, so actually more than one college there, California State University, San Marcos, Dominguez Hill, and San Diego State University. And not just we're going to work on these campuses, hopefully engaging with the students there, but we're also going to work with technology vendors and partners. We're going to implement the technical, the technology that we have been developing as an R&D tool into their commercial products in the field. And this is an invitation for everybody who's interested in implementing Guideline 36 or demand flexible controls in their building because they want to participate into demand response programs. We now developed very cutting-edge tools that allow you to program these sequences in a much more efficient way than going in the basement and coding the control system line by line. And so we invite, again, everybody who's here to reach out to us and work with us on this future project. And that's my last slide. Thank you, everybody.
Thanks so much, Marco. That was really relevant research on heat pump optimization, and it was really interesting to hear about your work with various campuses on different energy efficiency efforts. So I'll now introduce our next speaker, Xavier Gabarrell. Dr. Gabarrell Durrani is Vice Rector for Campus Sustainability and Professor in the Department of Chemical, Biological, and Environmental Engineering of UAB. And he's the former director of the Environmental Science and Technology Institute, CTA UAB. He also directs the Sostenibra Industrial Ecology Research Group and the Fertile City Project. He is an expert in LCA, MFA, industrial ecology, and waste management.
Yes.
Welcome. We can see you now.
Yes. Can you listen me?
Yes.
And can you see my screen?
We can see you and hear you perfectly.
Okay, so first of all, today I would like to express, before to start, my solidarity, the UB solidarity with Valencia, and my condolence for the victims of the storm and floods that seriously affected the Valencian region in Spain last 29 October. And this is because this is the largest natural disaster ever seen in the region, in Valencia, in terms of material damage and human life. This flood have accounted for more than 200 people die, and we don't know, we will see it, 50, 100 more people disappear. And this is not only due to the climate change in this case, also due to some politicians' decisions they didn't alert of the recent time. So first of all, here, all my support for them today. So starting my presentation, I introduce first of all, how is our university and our campus that we consider itself as a living lab or a lighthouse to experiment with the new technologies and guide cities. We developed a program for healthy and sustainable campus. You can see here in the picture so sustainable and healthy campus in Catalan. And projects such as the Easy for Climb, a European competence framework for a low carbon economy and sustainability through education, among others. In this case that you can see in the picture, there are different partners and different buildings involved, or other projects like Curricular. So I will stop to explain a little more the data or the environmental science and technology building and this case study. And then I talk about the energy consumption, of course. So where is our university? You can see here Europe, no? The world and Europe and the Barcelona metropolitan area. So our campus is 20 kilometers far away from Barcelona. And in this metropolitan area is where, in the Barcelona metropolitan areas, where we have the UIB campus. So located in Barcelona, and at international level, we are not the best, but in rankings we are not in bad positions. Sorry. The UIB in figures that you can see here, founded in June in the last century 68, so we have a 50 years old campus with 35,000 students, so undergraduate plus master students, and almost 5,000 PhD students. So we have about almost 5,000 teaching and research staff, and administration and services staff, 2,300. So this is a community of about 40,000 people. So a small city with forests around us. If you see the picture, you can see two main routes that close our campus. The campus also has 2 villas for students and visitors, farms for animals, and 2 train stations that each one is from one company exploited for different companies. So this is where we are in 260 hectares, but you can see that it's a compacted campus where we are living. So, as I said previously, we started here in the campus, although the university started in the 68, we started in the campus in the 71. Therefore, our buildings were 50 years old, more or less. Mainly built with concrete, but windows. In that moment, the construction in Spain didn't use good materials without any criteria for sustainability or any criteria for insulation systems. On the top right, you can see also a construction with containers that also without any thermal insulation system. So with the reality, our main direct energy consumption, as you can see here, came from the electricity, followed by the gas. So the main use of electricity are building cooling systems in summer, lighting, IT servers. Yes, this is an increasing, every time is increasing. And the main use of gas are related with the building heating systems in winter. So in summer, we need cooling, and in winter, we need heating systems. But where we are moving, so this is the newer building. You can see here that since October 2014, ICTA-UV, that has this new building. So this is a building that satisfies high energy efficiency standards, reflects the open, transparent working environment characterizing the institute. In this case, the objective was clearly focused on sustainability. So this is a different building from the others in the campus because the objective was clearly focused on sustainability regarding water, energy consumption, as well as the building materials used. As in the former presentation, the building achieved the LEED Gold, not platinum, certification. But one of the characteristics of this building is the outer facade of the building that contains a bioclimatic skin. If you see the building now in the picture, maybe you can see a greenhouse. And this is one of the characteristics of this building. So this is a comparable to a greenhouse which regulates the storage of solar radiation and ventilation through a series of automatic openings and closings. It's using also this Siemens monitoring and automatic system. So its outer skin open and close automatically depending on the temperature, humidity, wind, or sunlight, in order to offer the best bioclimatic conditions inside the buildings at all times. So thus an intermediate area with temperatures between 16 and 30 Celsius degrees is created between the outside and the inside. This is what we call the bioclimatic skin. So with this, we can create, we can maintain temperatures of comfort in the working areas, and at the same time, it reduces the energy demands and improve temperatures inside. Theoretically, at the beginning, was accounted that we can obtain about 60–80% of energy consumption. We can reduce our energy consumption about 60–80%. The building has also another characteristic, that is the rooftop integrates is integrated with the building. So there is an interchange of flows between the rooftop and the building. And you will see in another picture later that this allows to save also energy consumption in summer and winter. Inside the building, also there's located a greenhouse gas monitoring station that is part of the greenhouse monitoring network in the metropolitan area. So we follow CO2, methane, and other climatic parameters. Those data is available to at the ECOS portal and is used by master students as well as PhD students for different purposes. So, as I said before, with the bioclimatic scheme, the building is reducing or saving 60–80% of the energy consumption. But in this picture, you can see the change of flows, the air flows between the building and the rooftop, and this interchange is bidirectional and flows from the rooftop to the building. In the rooftop, we are producing vegetables in that area. With this, this allows us to reduce also, in red color is reductions in heat reductions, in blue color cooling reductions. So we can reduce or cut off the the energy in summer as well in winter, more in winter than in summer. I had numbers also in euros, but I think that maybe it's better to show or to see the kilowatts square meter that we can save in winter and summer. I think this data has not provided before. The floor of this building has about 512 square meters. So we have a 50 years old campus, and what are doing now in terms of decarbonization. Later I will talk about our policy, but in general, what we are doing, reduce the energy consumption and demand through the LED technology, automatization of buildings, improving buildings envelope. We have an investment plan, and every year we are introducing more PV panels, and so our self-energy production increase every year. And of course, campaigns related to the energy. One of the things that started in the ICTA building was the use of fans in our offices. And currently, now, in the last year, we started to introduce fans in the classrooms and other rooms in the campus. You can see here that this is a big room. And another characteristic that I want to remark here is because we are as a lighthouse. In our campus, there are 4 types of renewable energies. So the solar photovoltaic that I talked before. The biomass, so the main energy production that we have is the kind from biomass, biomass installed in our gym, in the physical activity service. Also, we have solar thermal energy to heat sanitary hot water. And finally, the ICTA building has geothermal energy. This is not common in Spain to use geothermal, but we demonstrated that we are saving a lot of energy using the geothermal. This is another picture about the fans. In this case, in the boxing area, no, in the gym, big, large fans. But now, a few minutes to talk about our policy. So, as a university, we recently approved the University Climate Policy Program. So, this plan aims not only to reduce the consumption of water and energy, but also eliminate the use of fossil fuels and advance in reduction of indirect emissions caused by our activity. So our objective is to achieve the climate neutrality next 2030, and of course, with the compromise of also compensating for any greenhouse gas emission that cannot be reduced, but that because sometimes that happens. So our objective is to gradually reducing those emissions, abandoning the use of fossil fuels with total replacement by renewable energy by 2030. We know that this is a challenge. I showed numbers before that we are using gas for heating, but this is our challenges. More numbers in 2018. You can see here UEB achieved a significant reduction in our carbon footprint because we began pushing electricity from renewable sources. So all the electricity that now we are using come from our self-production, or we purchase from renewable sources. So here, why in 2015 total emission were about 40,000 tons of CO2. Last year was lower to 24,000 tons. So this is a good reduction. So in general, 79% of the greenhouse gas emissions were generated in total by mobility to travel to the campus. I explained we are living or we are working in the campus 45,000 people, but only living, the number was in the picture, in the slide, only living there 2,200 students and visitors. So the main contribution, scope 3, is due to the transport, the mobility, and that's account about 79% of the greenhouse gas emissions in this moment. 12% is generated by the gas consumption in buildings, and 4% by what we have in the category by business travel. So for us, it's strongly important in order to achieve the challenge, the reduction, and to share with the community our objective. And this is one of the reasons because this year, so this academic year, that the academic year that we started in September, so 24-25, is dedicated to the need to minimize the use of fossil fuel. So let's reduce the use of fossil fuels. Under this slogan, we organize several activities during all the academic year. One of these activities has been the second edition of the UEB Science Carriage that I will explain later. And another activity was the inaugural lecture given by Dr. Kevin Anderson. So when we start the academic course, there is a person that has the opportunity for the inaugural lesson, in this case, Kevin Anderson. I am finishing. So this is the slide that I comment before, the carriage. So this the carriage is we have 2 train stations in the campus, and 1 train that is going to the university several times per day. Contains information and illustration related to the reduction of fossil fuels consumption. Also, it contains audio guides, podcasts, and so on, in order that so hundreds of thousands people that use during the year that train can have the opportunity to learn at the same time that is moving to the university. And I finish with this slide. This is, we changed our main street that was designed to be used by the cars for pedestrian users. And this is what we talk about. This space is called Campus Healthy and Sustainable. And thank you.
Thank you so much. That was truly a global example of living labs in Spain. So really interesting examples of the different energy efficiency features of your buildings, and it's cool that you're able to use geothermal. So with that, we'll move on to the Q&A portion. We did get a few questions in the Q&A box that I will share with presenters. The first question was for Melody. Does the double skin of your office building have the ability to create electricity by PV?
So I actually had a student I co-advised a master's thesis project that dove a little further using computational fluid dynamics, looking at, because my understanding is the way energy modelers, and they kind of just fudge factor the solar heat gain coefficient and the U value of the given the double facade, but they don't really know, how much of an insulating factor it is. And even if they do put thermal breaks in there, it can also act like a heat sink. And also it kind of, if you want to have natural daylighting, you have to kind of study that as well. It has operable motors that open up some of the panels to supposed to look at the climate and the conditions to determine when it's more optimal to have the panels open or closed. I know there were some issues with speccing the motors on those out, and I don't think they're automatically controlled. But in terms of, there's no PV on them, so there's no, electricity production, only the architect claimed a certain percentage of efficiency gains. But again, I think that was just from energy modeling. And we have facade experts that have PhDs in consult on facades, and they know that oftentimes, the energy modelers just kind of fudge factor these parameters inside their models. So we did a more extensive master's thesis where we looked at sort of different computational fluid dynamics of different wind speeds, fenestration, and studied this a little bit more. And our study found that it's really site specific how much a double facade will work, how much improvement you'll get. It's very site specific. And so you really need to study it, not just putting the fudge factors in and assuming you'll get those gains. That's what we found. And we also found that, in some locations and conditions, just triple pane window can serve just as well, if not better, at a lower cost. So, but I know there's a little bit of detour from answering the question related to, I think it's also an architectural feature. So that has to be a discussion with your client in the design, how much energy savings are you going to get and what's the return on investment when deciding whether or not to have that in there. But there is no PV on the panels.
Thank you. For Xavier, are there any efforts to utilize the sensible heat rejection from the IT spaces that you mentioned so that it could provide comfort heating to other buildings?
Yes, this is one of the things that we are monitoring currently. We are monitoring, and we try to centralize, but sorry, not centralize, with a distributed systems to centralize the IT servers in order to put in rooms that will not need cooling systems. So in order to reuse or use the environmental conditions. So in the this is, for example, with one of the things that we have in mind is to combine the gym, the service for physical activities with the IT systems in order to make a symbiotic relationships of flows. I don't know. So as they needed a specific temperature, but they produce heat, that heat can be used, for example, in the swimming pool.
Yeah. And one more for you. Do you know the cost payback on the building's exterior bioclimatic environmental response system?
The cheaper building in our campus, the cheaper one. So the point of the payback, no, the answer of the question is exactly no. But when we compare the cost per square meter with the other buildings, is the cheaper one. So the question is, what is the payback for a building in a university? Because the total cost we are counting when we account for the cost of the building, that includes all the monitoring systems, automatization, and so on. So what we are comparing is the cost of a square meter. It's cheaper than the others built in our campus. And well, yes, this is the cheaper. Mm-hmm.
Great, thank you. And one for Marco. Seems that Berkeley Lab has pretty far reach with a lot of its different projects. Can you give us some insight on how you determine which campuses to partner with?
Yeah, so it's typically the people you talk to and you know. And so that's what kind of my sort of opening this up to any campus that wants to collaborate with us and we know could be a good fit for one or the other projects. And so in addition to students, also location is important, could be in, you know, IOU territory or not, may have some features, some technology. So really like personal connections. And I know, you know, a few campuses, but not all of them. So.
Got it. Well, that's all the questions. I didn't want to acknowledge that there was just one more comment in the Q&A box for Xavier. The person just said, thanks for recognizing the crisis in Spain and the extreme flooding. And that's just an example of how climate change effects can really affect us globally. So thank you for that. But those are all the questions that we had. We really appreciate all the speakers providing time to give us those thoughtful presentations. So with that, I'll turn it back over to Isabella to move on with the agenda. Thank you.
Thank you.
Bye. Thank you.
Bye.
All right. Thank you, everybody. Thank you to our panelists and everybody who asked questions. So now we're planning to have a lunch. So we'll start a little bit early and then we'll reconvene at 1:15 for our next short feature. So go enjoy lunch.